Good afternoon, everyone. This is 5.4, Eulerizing and Semi-Eulerizing graphs. Now, basically, we saw in 5.3 that some graphs have, basically the ones that have all even vertices have an Euler circuit, which means that they can walk around the graph and start at one point, walk around and hit every single edge of the graph, and then come back to that same beginning point, and go over all the edges only once and only once. And that was wonderful. And that's really great for police officers that want to walk around the neighborhood, that don't want to do any extra blocks that they don't have to do. That's great. However, and sometimes what if there's graphs and routes that people have to take that don't have an Euler path or an Euler circuit? So what we can do is we're going to learn in 5.4 the method for adding at the fewest number of streets, deadhead streets, which means, I think they mean the word deadhead. They mean having to recross that street or edge. So we're going to learn how to do that in this section. And it says, when we can't cover every edge of a graph exactly once and only once, we must determine which edges we will cover more than once to maximize or minimize, the amount we have to walk through a neighborhood. To do this, we Eulerize a graph. That's what Eulerize is. This means we duplicate existing edges to make all vertices even. We find the optimal Eulerization by duplicating the least number of edges. This leads us to find the most effective route, called the optimal route. The route is found by Fleury's algorithm, and you label each step of the path, 1, 2, 3, as before. A semi-Eulerization of a graph means to make all the vertices even except for 2. So when you do that, that is going to make it have an Euler path, but not an Euler circuit. So that means you can travel throughout the entire neighborhood, going over every single street once and only once, but you're going to start and begin in different places. Right? And so you're going to add duplicate bridges. When you Eulerize something, you're going to duplicate certain bridges or edges, but you're gonna leave 2 odd vertices still, the beginning and starting point, beginning and ending point. Okay. All right, let's see the first example. A new business owner wants to deliver grand opening flyers to each house on the street of the neighborhood shown in the figure below. There are there are 2 people, so we will walk only once along each street. And then they ask us, can every street be traveled once and only once? That is, does a Euler circuit or Euler path exist? So, it says there's 2 people walking. So I guess what's going to happen is, if there is a left side of the street and a right side of the street, like you see right here, like on this street, there's the left-hand side of the street we have to deliver flyers to that side, and then there's also a right-hand side of the street. So when that happens, one person will go to the left, one person will go to the right. So we only have to pass that street one time. But when you come to a street like this, there's only one side, they're just going to walk together. I know it's kind of it's wasted effort or whatever, but they like being together anyways, and so they don't want to separate. And so that's how we'll just say this problem. Okay. And then that's probably not effective. You're paying 2 people to hand out flyers. You wouldn't want them just walking together on one street. But we'll just for the sake of making a graph to fit this problem, we'll just say that that's the case and to simplify it. All right. So if that's the case, then we need to go on every street in this neighborhood. And we're going to say just for, I'm going to say that they don't need to walk around the park because there's no houses there. So I'm just going to, just for this problem, we'll just say that they're not walking around the park. Maybe there are people in the park that we could be handing out flyers to. So we'll see in the next problem. I think we do walk around the park, but just for this one, I'm just going to say, let's not walk around the park. Okay. So I'm just going to make a vertex at every spot where they have a choice to go left or right. I'm just going to make a vertex. Throughout the neighborhood. And then I'm just going to make for every, road or street that we see here, I'm going to make an edge that they have to travel on. And like I said, I'm going to make one edge, whether there's two sides of the street or one side of the street, because like I said, we're just going to simplify this problem. All right, I believe I traced every street and oh wait, I missed one on the bottom here. Okay, I can just go along the outside. I traced all the outside of the neighborhood and then now like the inner streets. Let me just double check. It's important in math, the double checking part. A lot of people like, oh, I want to just go on the next problem. Like the double checking part is important, right? Just to make sure that we've just written the problem down correctly to begin with. Okay, now that I have it like that, all these little details, like the buildings and stuff are kind of distracting a little bit. So I'm gonna try to grab everything and like just pull it away. There we go. And now I'm gonna go ahead and count all of the, I'm gonna find the degree of all the vertices. So that's 2, that's 3, that's 4, that's 3, that's 2, 2, 3, 3, 2, 3, 1, 2, 3. Okay. 1, 2, 3, 4, 4. All right. And then I believe I labeled every single verse. Let me just like kind of go through it. Like here's my double checking again. All right. It looks good. Now I need to really pay attention to the odd vertices here. So I'm going to change colors and put them in red. I'll listen. So I'm going across the top. I noticed that I have 3. Oops, I need to erase it. Let me just go through, make sure all my even are blue and red are odd. Okay, looks good. Okay. Because remember, Well, automatically, I noticed that they asked, can every street be traveled exactly once? And it is there an Euler circuit or an Euler path that exists? And the answer is no, right? And that is because there's odd vertices. And there's more than two. There's not two odd ones. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 odd vertices. So there is no Euler path or no Euler circuit. But these people still want to hand out the flyers in the least amount of way. So now what we need to do is we need to find each pair of odd ones and see and connect those two odd edges. And we'll pick the ones that are the closest together for one thing. And then try to connect them using the least amount of edges as possible. So see, these are like next door neighbors, like these threes are right next to each other. So very easy is if I just like make an extra line between these two neighbor and they asked us to find the optimal Eulerization. And if they want you to do Eulerization, they want you to find an Euler circuit, which means they want you to add the extra edges until there's no odd vertices. So I'm going to go ahead and connect every pair of odd vertices, and I'm always going to try my best to connect the ones that are closest in proximity to each other. So that's why I chose down here, I connected the two threes. Now, if you see, notice it's 1, 2, 3, 4. This is now of degree 4. And this is 1, 2, 3, 4. This is now of degree 4. So they're no longer odd vertices. That's what's great when you just connect two odd ones, they both become even. And I only did that with one extra bridge, two birds with one stone, right? Next, I'm not sure if this will, I don't think this is gonna work. Let's just try to do this. Notice how if I connect this one with this one, now I protect the next two odd. Now let's make sure that I think I'm pretty sure now that this is the wrong degree. So look, it's 1, 2, 3, 4, 5. So then this turns this one back into an odd one again, and I didn't want it to be odd. So you have to get one. I've already connected this 3 with the one above it. So like, I don't want to connect that one to another odd one. So I have to find another partner for this vertice to connect. And so the closest one that I see, like in proximity of that one, is like this one up here. Well, so I'm trying to find a partner for this one. So I see this one is the next closest one. So maybe what you're thinking is maybe I could just go straight across here. But the problem is that I'm going through all these houses, right? That's what I'm doing. And there's no place for me to even walk there. I can't just, I don't know. I can't go through somebody's house. Like, so I can't go. And that's a big thing when we Eulerize something, I only can go on streets that are already, or edges that are already in the graph. So I can't go just a straight, that would be ideal. I'd be adding only one more edge, but that wasn't one edge that was originally in our picture. So that's why I have to add 2 edges here. And I can either go up to 4 and then go over to 3, or I can go over to 2 and then over to 3. But I have to connect those 2 odd ones, and it's going to take me 2 bridges instead of 1 to do that, but that's the least amount. There's no other way to connect those 2 ones without using a fewer amount of bridges. So that's the optimal way to connect those 2. Okay, then the next thing is I have to do the next 2. And I just I'm gonna do the same thing here. I'm gonna go add one here and add one here. And I connected those 2. I connected these 2 3s by adding 2 dead weights there. Then I can connect these 2 by doing one extra run of that street. Then I can connect these 2 by doing here, well, maybe here and here. Oh, I can go through 4 too. That would have been fine to go like this. But I had to connect those 2 close proximity odd edges. And I couldn't do it in one edge, so I just used 2. So that's fine. And then I have the last 2 odd ones, and I just get to draw one between them. But let's just double check that now all the vertices are even. That's what Eulerization is. It's when you make you add extra edges, the fewest amount that you can will be optimal. But then now we add these extra edges and now all vertices are even. So let's just double check that's actually the case now. So I go through, and the ones that were odd, now this is a 3. So now I can count 1, 2, 3, 4. Now it's a 4. 1, 2, 3, 4. Then now this one is a 4. 1, 2, 3, 4. That one's a 4 now. 1, 2, 3, 4. Now that one's a 4. And I could even double check the ones that are not, that I connected between, so this one used to be 2, but now it's 1, 2, 3, 4. So now it's still okay. And you'll find if you have to go from one odd edge or one odd vertice to another, if you have to travel through another point, that's fine, because you have to go to that point, which is going to add 1 to the degree, and you have to leave that point, which is going to add another 1 to the degree. So you're going to add 2 to that degree as you go through a second location to get, to the next odd vertice. So you see the same things happening here. So that's 1, 2, 3, 4. So that's now 4. That's 1, 2, 3, 4. That's now 4. Right here, I changed that degree, but it's 1, 2, 3, 4. I changed the degree here. It's 1, 2, 3, 4 now. That's 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Now it's 1, 2, 3, 4, 5, 6. This one in the middle is now 6, and then 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, and 4. So you see that now with the added edges, every single vertex is now even. So, and because I did it by just trying to find the 2 odd ones that were the closest together, and ideally whenever I could connect 2 odd ones by just one edge, I did that. And then if I didn't do that, I only added 1 more edge if it was just not possible. So this is the optimal Eulerization, is this graph that I'm showing you here. And they ask us next, what are the minimum number of streets that must be covered twice? So for every pair of odd vertices, I had to add at least one edge, right? If you see it right here, look at this. These 3s in the bottom right corner. For I had a pair of odd vertices, I can add 1 edge. I mean, that would be ideal if every time I have a pair of odd vertices, if I just added 1 edge, that would be the most ideal thing to do. So we had a total of 12 odd vertices. So if I just used 1 edge to connect all those 12, that means I would have had to 12 divided by 2 for every pair of odd vertices. I'm going to need one edge. So 12 divided by 2, then it's 6. So the least, let me write that, the total number of vertices, which was 12, divided by 2, because for every 2, I need at least one edge. So that means 6. So there, so a minimum of 6 edges has to be added. To Eulerize that picture. All right. Excuse me. All right, going on to the next one. They say here, find an optimal route for the flyers to be delivered. Describe the routes by labeling the edges 1, 2, 3, and so on in the order in which they are traveled. So I noticed with this problem, one thing is I noticed that they actually, this street, they actually have that in a graph. And every single one of the answers, ABDC answers here, see how they have, I'm sorry, this street right here, the streets around the parks that I did not include in my graph on the last problem, they have included them. So here, and I'm going to say for this problem, we are walking around the perimeter of the park. We're not walking through the park. We're walking around the perimeter of the park, handing out these flyers. Also, it says find an optimal route for the flyers to be delivered. I'm going to say I'm going to add that where we start and begin at the same point. Because I feel like this problem just isn't as clear as it should be. So to make some clarity. So I'm going to write including. And I mean, if I could, the way I figured out we had to be including the around the park for this particular problem was because one of these has to be correct, and but they obviously they have those roads around the park. So that's how I knew that, and that's what they did. I kind of understood what they meant more deeply when I noticed the answers. So sometimes I guess you have to do that when they're not exactly clear. And I apologize for this problem being not as clear as it should be. Hopefully your homework's much better. Much better. All right. Okay, so I'm going to say including around the parks. And I'm also going to say, let's go ahead and let's find a path where we can start and begin at the same point. All right. So they want us to find this optimal route to put the flyers out, and they want us to describe the route and so they give us an A, B, D, C answers we have to choose from. And we're going to kind of cheat with this method, and we're going to be like, we're going to be doing exactly what we did in the last time. We're going to Eulerize the graph. And then we're going to pick which picture best fits our Eulerized graph. And we're not going to worry about this pot and the numbers, like these little numbers that they have on here. We're not going to worry about that so much. We're just going to worry about, which one matches our Eulerized graph. Because I think it's just too much to actually map out using Fleury's method to double check these, and we're just not going to do that. We're going to find the one that fits we're basically just going to do what we did in this problem and find the graph that best fits that. Okay. You got to kind of, sometimes when you're doing math homework, you kind of have to think about the section that you're in and just kind of mimic the requirements that they're asking you to, that here we're focused on Eulerization. So I'm just going to assume that if all I do is Eulerize the problem, that I'll be okay. They're not going to ask me to do extra things after that. Or for a problem like this, if all I do is Eulerize the problem, that then the solution will come to me because it's an ABDC answer. And that's what happens here. Sometimes that's mostly true, but sometimes they want you to review from previous chapters as well. So anyways, let's get started on this problem. So what I do is I like I said, I put a vertice at every place where if someone were walking around and they have a choice to go left or right, then I put a vertice. I am putting vertices around the outside of this park because, like I said, we're going to be traveling around the outside of the park. And for this one, unlike the other problem, I'm going to add one more thing to this problem. We don't have two people. It's just one person walking around. So they're going to have to make double. They're going to have to go up on the left side of the street, and then they're going to turn around and go on the right side of the street too. So only one person handing out flyers. All right. So that would mean that along the outside, we only have to go on that street one time because there's only one side of houses. And around the park, I'm going to say we only have to go around the park one time. So I'm just going to go all along the outside of the picture. I'm just doing a single line. Now, around the parks themselves, there's only a single. Oh, I forgot my vertice here. There's only a single line around the edges of the park. All right, now it's between the outside and the inside of these city blocks where now we have left and right side. So I'm going to draw two lines for these inner streets. So in any street that's in the interior of this, that two sides, two sides, two sides. I believe I got all of them. All right, and I believe I got all my one-sided streets as well. All right, so I think that's my picture. So let's get it away from the actual picture. So now we can count the vertices more easily. There we go. Now, so like it's just in a different color, I'm gonna write the degree of the vertice on each one. All right, I'm just gonna go through all my vertices, double checking that I got all of them and labeled. All right, I believe I got all the degrees of all of mine labeled. So now the question, now I just find out where the odd degrees are. And I notice that I have odd degrees here, 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 and here. And let's just double check. Yeah, okay. Oh, wait. Oh, and why did I erase that one? I think I didn't mean to do that. Anyways, okay. So there's 4 odd vertices, and that would mean there's not an Euler path or Euler circuit. But if we connect, if we add extra edges to connect the 2 vertices right now, all the odd vertices, or each pair of odd vertices, then we're going to have an Euler circuit. So I'm going to go ahead and add. I'm going to add the most obvious one is these 2 are the closest. Like, notice here, these 2 are the closest, and they're already connected by just one bridge. So I'm just gonna, or edge. So I'm just gonna add it in here. That's one that we're gonna add, and then notice that like these 2 also need to be connected. And of course, I can't go on. I mean, technically, we're going across the street. That might actually be possible, but in our graph theory, if there was not a road drawn there, then like we assume we can't take that path. So we're gonna add an edge here. So you can only replicate existing edges. So that's not one that we had drawn. So like we are gonna go from 2 to 3 and then to 2 to 3 on the top. And that's how we're gonna add those 2 edges and then all of them are gonna have even. All of them will have even degree. So let's just double check that. So I look at this vertice and I say, okay, well, it has 1, 2, 3, 4. Now it's no longer a vertice of 3, a degree of 3, it's 4. So 1, 2, 3, 4. Now that one's 4. Now this one right here that I changed is 1, 2, 3, 4. This one in the middle was 2, but now it's 1, 2, 3, 4. Now this is 3, and now it's 1, no, 1, 2, 3, 4. So now they're all the odd ones and are now even, and the even ones that used to be that I did something to, namely this one, it is still even because I added 2 to the degree. So now our job is to look at these other pictures on the bottom and kind of try to look at them and figure out which one is ours. So I'm really looking at where I added the edges. These red edges, I'm looking for the graph that has the edges added in exactly the same spot. So maybe if I make these a little bigger, you'll focus more on what I'm talking about. So I'm looking for where there's double edges exactly in those three spots. So like I look at B and they have a single edge between right here. So I have a double edge, this one and this one, it only has a single edge. And I mean, if they didn't connect it going this way, they could have connected it going this way, making it a lot more edges, which would have not been optimal. But you can see that they didn't do that. They didn't connect this one with this one by going that way either. So it just looks like they didn't realize, whoever did this one didn't realize that we needed to connect these two vertices, you know? And they also did not like connect this one. This would be way optimal, but with this one, they also didn't do that. So we don't see like double edges all the way there, you know. We see double edge here, but we don't see one like here going, you know, like so. It's like when you are Eulerizing something, you're adding an extra path, you know, from the two odd vertices. So it looks like B is just not correct. I look at D, the same thing. I do not see double edges. I see a path that they went straight from 3 to 3, the odd vertices, but like I said, that wasn't a original path, so that's not the right answer. You can't add edges that were never there in the first place. So, and then this one C, the same thing. There's not a double path here and here. There's not a double path. So I would say that D is wrong too. So the only one that looks like they added the same double pass like I did is A. And I also double checked and I noticed that their picture overall looks exactly like mine. And if you want to right now, you could kind of just go through all the numbers, like go through the actual path 1, 2, 3, 4, and just make sure that it goes all the way around. But I don't think that's necessary because we already know that B, D, and C are wrong. So A is our correct answer. Okay. All right, moving on. And this one doesn't take very long, so don't stress out. So this one says find the optimal semi-Eulerization. So semi-Eulerization means that we're going to add extra edges until there's two odd vertices. So we're not going to add quite as many extra edges as we have when you Eulerize something. So first step, I have to go around and I have to figure out what is the degree of all the vertices. Because I need to know where my odd ones are, so I know where to add my extra edges. So 2, 2, 2, 2, 2. Then 3, 3, 3, 3, 3. Then 3, 4, 4, 4, 3. Then 3, 3, 3, 3, 3. And then 2, 2, 2, 2, 2. All right, so let's highlight the odd ones. And they do say that they want us to find the optimal semi-Eulerization for the graph when B and C are required to be the starting and ending points. So we want to keep B and C still odd, and we're only going to make all the rest of them even. But we're going to add extra edges to make the rest of them even. So I noticed that that these are my even ones or my odd ones. So here, oh wait, I'm going to keep that one blue because I'm not concerned with it because that's the one that we want to keep blue. It's only the ones I make red that we want to change. Mhm. And you should always have an even number of odd vertices, so we can just double check to make sure we kind of did it right. And I didn't do my double checking on this and just making sure that I actually went through and found the degree of every vertices. So I have 1, 2, 3, wait, 1, 2, 3, 4, including we need to do this one too, but including the blue threes, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Wait, 12. I think this is this one too. So I believe that we have 12 odd vertices, and that you can never have an even amount. So that it's just a helpful thing to know, so you can double check to make sure you're counting correctly, or you didn't miss or recount one of the vertices. So every red one I need to make it an even one. So the one I noticed right away is like the one that's not as close to the others is this one right here. So I'm going to try to connect that with the least amount of edges. And I can't go straight there, like I said, because it's not an edge. I can only duplicate already edges. So I'm going to go here and here. And then I need to connect these two. So I go like this. And then I need to connect these two. So I go like this. I connect these two. So I go like this and like that. And I think that we have semi-Eulerized this graph. Just double checking all the red threes are connected. Yeah, I think and so we can double check that everywhere around all the spots where I put a, I changed by adding an extra edge. We can count and make sure that they're well, actually all but B and C should be even. So like this one is 1, 2, 3, 4. Now it's an even vertice. So 1, 2, 3, 4. That's an even vertice. This one is 1, 2, 3, 4, 5, 6. So now it's still even. 1, 2, 3, 4. It's still even. Or now it's even. 1, 2, 3, 4. Now it's even. 1, 2, 3, 4. 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 1, 2, 3, 4. 1, 2, 3, 4. So now all of the odd ones are even, and even the ones that were originally even that I had to go through, those ones are also still even. So the only ones that are odd are the ones I didn't touch is the B and C. So we should have, this is the Eulerization of this picture. And so let's go back and answer the question they ask us. They say, find the optimal semi-Eulerization of the graph. So I know it's optimal because I found the ones that were close together, and as many as I could, I just added one duplicate street only. And then when I couldn't do that, I at most just added one more. And I didn't go out of my way, So it is the optimal semi-Eulerization of this graph. And then it says how many edges must be duplicated, number of blocks twice. So I had now let's like how many red ones did I add? So 1, 2, 3, 4, 5, 6. So 6. So like 1, 2, 3, 4, 5, 6. Yep. And there we go. There's our answer. All right. Thanks for listening. Let me know if you have any questions. Bye.